Hi, everyone, and welcome to the third part of our series on hacking and securing multi agent systems. So, in the first two parts, we looked at building a multi agent system. We used the Crew AI library to do that. And then in the second part, we looked at attacks that can happen in that kind of a setup. More specifically, we looked at prompt injection and we also looked at sending agents into a loop. Now, all of the stuff that we've seen so far, whether it's the CSA Agentic AI red teaming attacks or the OASP top 10 for Gen AI, now all of these attacks that we've been exploring through all our videos so far, each of these becomes so much more worse in a multi-agent setup. And let's take a look at why that is so. So here are some very interesting statistics I gathered from this paper that's available. The link will be in the description below. It's also there on the screen, which talks about how many LLMs the researchers were able to find vulnerable to at least one attack vector, almost all of them. 82.4% models were compromised through inter-agent communication. 52 were vulnerable to RAG backdoor attacks, and 5.9% only were resistant to all attack vectors. In fact, only one model from the entire sample set that the researchers tested was found to be safe from all of these attacks. And all of this becomes, like I said, much worse in a multi agent setup because now you have agents calling other agents. And the kind of validation that we would expect, or the kind of authentication that we would expect, let's say in a user to agent or a user to system communication, goes away when it's agents that have the autonomy to call other agents, and they also have the autonomy to call tools to meet with the user's objective. The key issue that we find in all of this scenario is that the system context, the prompt with which you create your agent or your MCP, the task and the backstory that you give, gets mixed up with the user context coming in from either the user's input into a text box, or from a document that the system reads, or from additional input that I give from an HTML file or an image. So all of these result in the user context and the system context kind of getting mixed up. And this is where a lot of the multi-agent complexity comes into place. So what was kind of simpler in a single agent setup becomes much more complex when you have a user calling agent A, which could call agent B with no validation, no signing, no authentication between the two agents, which then could call agent C, so on and so forth. And therefore there is this autonomy, there is access to tools, there is trust between agents because they all belong within the same ecosystem. There is memory, once poisoned, will persist across multiple agent calls. There is communication interception that can happen, and there is all of this complexity now that gets added into the whole setup. And as all of us in security know, that complexity increases the security risk potential. And so from the same paper, we see that direct prompt injection, RAG backdoors, and especially inter-agent exploitation has a very high chance of success because of the implicit trust boundaries in the whole setup. We've discussed this agent-to-agent prompt injection. Malicious output from agent A becomes weaponized, becomes an input to agent B. Malicious data can be crafted. Agent A processes that data, contains the malicious instructions, which then go to agent B, and that's what the output shows up. We looked at this example where we had the researcher agent reading malicious instructions from an HTML document, synthesizing that, giving it to the writer agent that quoted that content verbatim from the original HTML source document. Now, this can happen in JSON fields, it can happen in image data that looks benign but has little perturbations that are not visible to the human eye, and it could also be split across multiple interactions. Similarly, privilege escalation is possible through agent chaining. There is currently no accepted authorization model between agents. There is implicit trust. There is no defined role based access control RBAC, and it is not, of course, mandatory to do logging of all the activities that your agents undertake. Agents can inherit identities. We talk about non-human identities, and agents are part of that. Transitive trust, because agents implicitly trust the calls coming from different agents. Confused deputy, a low privileged agent tricks a higher privileged agent into doing actions which it was not supposed to do. And also forged requests can be sent forward. So all of these are possible attacks in a multi-agent setup. And also we looked at different design patterns when we talk about multi-agent architectures. And one of the design patterns was a manager worker pattern, where there is a coordinator agent that then has multiple sub agents that it can use and execute and call upon based on the objective. And so if this powerful coordinator agent was hacked, you can imagine the consequences that the system would face. And obviously it would become a single point of failure. Similarly, context poisoning, goal manipulation, memory poisoning, these are all possible, and these poisoned inputs remain static in the system as the system progresses in terms of its execution, and this poisoned data then flows through into downstream actions and downstream agents. And of course, there are different ways in which this can be done. Poisoning can be incremental, we can send it out in parts. Semantic poisoning, alter the meaning of the statement without changing its structure. Preference poisoning, and embed triggers for future exploitation and activation upon a particular event or timeline being reached. We looked at this other very interesting example in our analysis in the second video, where we looked at agent A calling B, B not happy with the output, telling A go back and do it again. A sends the output again to agent B, which is this super high standards critic, and he or they simply don't accept the output coming from agent A, and then this just goes back and forth forever. So imagine the kinds of impact that this can have, the least being token calls and wallet exhaustion. So in light of all of this, there's obviously been a lot of talk around how to build secure uh, agentic AI systems. We do not have a framework until a few days back, when Google just came out with Google and certain other companies got together and came out with a framework called the Agentic AI Security Framework. I very strongly recommend that if you are in AI development, you must look into this framework. We do not have yet a library to go with it, but I'm sure that that's coming soon. And it's collaboration of multiple companies. It has the following key elements summarized as basic: behavior certificates, declaration and enforcement of agentic behaviors; authenticated prompts, what's the prompt within the system and what is coming from the user, differentiating that; security boundaries, isolation of the untrusted user input and segmentation of external data; security meta instructions that guide the model and its reasoning; and definition of application specific rules and policies. And then this paper goes on to define what this kind of a framework would look like. It very clearly defines the problem statement, evaluates existing defense mechanisms and why they are not effective, or why they might be more complex, and then it defines what these instructions and security protocols would look like. So it defines as certain examples how would behavior enforcement happen. There would be a guard agent, there would be an agent spec using a domain specific language and a tool for behavior enforcement. There would be something called a progent, which uses a domain specific language for tool access control, so what tools the agent can call. Conseca would be a component that offers a framework for policy generation and enforcement. So these are all conceptual ideas that are outlined over here. As I said, the basic controls is how they've defined it and given certain analogies and what the core focus of each of these controls is going to be. So definitely go take a read on this. It's on this URL a2as.org, and very likely I have a feeling that this might become the gold standard for agentic security. So to conclude, the core security principles remain the same. There has to be zero trust between agents. Each agent has to be seen as a source of compromise and also a target of attack. Least privilege by design. Run your tools in as sandbox, as containerized, as restricted and controlled an environment as you can. Defense in depth, access control, audit trails, uh, input validation, output validation, the data that you're reading into your RAG, you're storing into your RAG, the data that you're reading as a source input for an agent to process the instructions from the human user of the system. All of these should be thoroughly validated. Audit trails, detailed logging and auditing of all of the actions of the agent, and resource limits and circuit breakers to ensure that your agents don't go into an infinite loop and exhaust your resources. So I hope you found this video useful as you go out and build agentic AI systems and start making sure that you build in these guardrails from the design stage itself and don't leave it too far into your development cycle. So as we always say in security, the effort that you put into building security from the design stage will result in a huge cost savings when security bugs don't get found in production. Thank you for watching. If you like this content, please like, subscribe, and share.